Bismillah Rahman Rahim. So, uh, the topic for this lecture is impedance. So, we need to know the relationship, phasor relationship for the voltage and current for the three circuit elements. Uh, for resistor, we have V is equal to IR, right? For inductor, we have V bar is equal to J omega L I. For capacitor, we have V bar is equal to I over J omega C, right? So from this we can find out the ratio of the phasor voltage to the phasor current for all the three circuit elements. So for the resistor, V bar over I bar is equal to R, right? For inductor, V over I is equal to J omega L, and for capacitor, V over I is equal to 1 over J omega C. So in general, this can be written as V over I is equal to Z, or V is equal to ZI. So this is basically, this can be is said to be Ohm's law in phasor domain. This Z here is called impedance. Z is called impedance. So as you can see, for the case of resistor, Z is equal to R, ZR is equal to R. In the case of inductor, ZL is equal to, for example, J omega L. For the case of capacitor, Z is equal to 1 over J omega C. So in the case of inductor and capacitor, it depends upon the frequency omega here. However, in the case of resistor, this does not depend on frequency. But in the case of inductor and capacitor, it depends upon frequency. So impedance is a frequency dependent quantity. So impedance in general is is frequency dependent, right? And one more thing, it is not a phasor, though it's a ratio of a phasor. It itself is not a phasor. So Z is not a phasor quantity. And like resistance, this is measured in ohms. Uh, it is measured, Z is measured in ohms, right? And resistance is the opposition to the flow of current in resistor circuits. Impedance is basically the opposition offered by the circuit to the flow of sinusoidal current. So impedance is the opposition offered by a circuit to the flow of sinusoidal current. So So as we have seen and also described earlier, impedance is frequency sensitive, frequency dependent quantity. So the opposition to the flow of current will depend upon the frequency of the circuit also. So for example, let us rewrite it here. ZR is equal to R ZL. For the inductor, the impedance is given by J omega L, and for the capacitor, this is given by 1 over J omega C. So the impedance or the opposition to the flow of current offered by an inductor or a capacitor will vary with the frequency. This is not case with the resistor. Resistor is insensitive to frequency. Its opposition remains constant. But for inductor and capacitor, the opposition changes with the frequency. For example, when omega is equal to 0, omega is 0 when we are considering DC sources, right? When we have DC current or DC sources. So when omega is equal to 0, you see ZL is equal to 0. So that means it's a short circuit. And ZC is equal to infinity. That is open circuit. So when omega is equal to 0, when the angular frequency is 0, or in other words, when we have a DC source, then the inductor behaves as a short circuit to that source, short circuit to the DC source, and the capacitor, it acts as an open circuit to the DC source. Or in other words, in a similar manner, we can say that when we have low frequencies, the opposition offered by the inductor is small, and the opposition offered by the capacitor to the low frequency is high. But when, for example, omega is equal to infinity, then ZL is equal to infinity and ZC is equal to 0. So that is open circuit and that is short circuit. So at very high frequencies, in other words, at very high frequencies, this inductor, it behaves as an open circuit, right? And this capacitor acts as a short circuit. So the opposition offered by the inductor to the high frequencies is high, and the opposition offered by the capacitor to the high frequencies is low. So this is the behavior of inductor and capacitor to different frequencies. So this was the impedance for the inductor and capacitor, right? But in a circuit, we may have a combination of inductors and capacitors or resistors. For example, we may have some circuit like this. Uh, right? So its equivalent impedance, as seen from here, um, will not necessarily be like this, right? It will be in the form of, for example, Z is equal to R plus JX. It will have this real component and one imaginary component. So this is a complex number. Impedance is a complex number, right? So, and this can be written in polar form as like this. So this is the real part. R is equal to the real part of Z, and it is the resistive part. It is the resistance offered by this circuit. And this X is the imaginary part of the impedance, and this is called reactance. This is called reactance. This is measured in ohms. This is measured in ohms, and impedance itself is measured in ohms. So when X is positive, for example, then this theta is positive here, right? And for example, if we want to find out the current I from a voltage V angle phi over this Z here angle theta, so it will be V over Z phi minus theta. So this angle, the angle of the current, will be smaller than the angle of this voltage here. So this is phi minus theta. So it means that the current lags I lags V when X is positive. So this is the behavior of an inductor. Inductor. So this is so this reactance then is called inductive reactance. So uh, when X is positive, it is inductive reactance, right? And when X is negative, in that case, Z is equal to R minus JX, for example. We have Z angle minus theta here. And if we wanted to calculate current from V angle phi over Z, this V angle minus theta, so that will be V over Z. So angle will be phi plus theta here then. So this angle is larger than this angle here. So in that case, I leads V, which is a capacitive behavior. So when X is negative, it is capacitive reactance. The behavior of the circuit is said to be capacitive in that case, right? Uh, Furthermore, as we have discussed earlier, R plus Jx can also be represented in polar form like this. Theta here, right? Z angle theta, and this Z, this magnitude is equal to R square plus X square root, and theta is equal to tan inverse X over R. And if we are given this polar form, we can convert it to the rectangular form, and Z R is equal to uh, Z cos theta, and X is equal to Z sine theta.